Well, I wondering an example of reinforcement learning.
Okay, I think we all are familiar with this example. This is a childhood. Basically, is when kids receive something for something. So in this case, it's a candy for doing something good, or
For
in
good actions, actually.
yes, is I think this is the best example because it represents everything in reinforcement: the
Yeah,
reward, the action, the environment.
yeah. Like actually, the mother is kind of part of the environment, no? And the actions is all the possible um, states that the child can be, for example, in the school or in the church, at home, or only dinner, you know. And the action is to do good or do bad something in that scenarios. And the father give him a prime or no.
A good treat. Yes.
Yeah. Something example coolest that I found is from the DeepMind. This is the Google artificial intelligence or something like this. They work a lot with machine learning, you know.
And reinforcement.
Yeah, and they create a Alpha Zero.
What is that?
That is a kind of sort of program that can game different games. For example, chess, shogi, and go.
Okay.
Shogi and go, well, actually, chess, all three games are very famous because they are for strategy playing. And yeah, that I think that is a cool application of reinforcement learning. Also, this is for games, also with artificial intelligence to make a robot to do actions, to care a patient, or maybe a car that drive himself. That are other examples. So I was wondering what is the mathematical framework for this type of machine learning.
Okay. I think is all of this theory for reinforcement learning is based on Markov theory.
Yeah.
Uh, Basically, what it says is like we don't care about the history or the previous state.
Mm-hmm.
We only care about the previous state or the last state. So
Yeah, that is the Markov property, no?
yeah, there's no.
That is something cool because to measure the probability stay, to stay in action t plus one based on the history, we only need to the last.
The ST, we don't need the all the history.
Yeah. Well, where is the Markov process?
Okay, Markov process is a tuple of S, which is the states, and P, which is probably a transition probably matrix, and this matrix is going to tell us what are the probabilities for, to go from one state to another state. So he's going to take this matrix. It's going to take this form, and we have to say that the sum of the rows is going to be equals to 1.
That's because it's distribution
Yes.
in every state. And yeah, and also it's only for one. This is a transition matrix for one step
Yes.
only. Um, why we are talking about for Markov property and Markov process?
Basically, it's because the solution for the problem is based on this theory.
Yeah, but well, let's let's see a example now.
Example, okay. So here we have, this is an example for a course. We are going to say that is a 3 days course.
Mhm.
So we all start at class 1 and have probability 0.5, 0.5 to go to class 2. And from class 2 we have probability zero point 0.8 to go to class 3, or zero point 0.2 to go to sleep if the class is boring. And at the end, if we pass the class, we have probability 1 to go to sleep.
Yeah.
Or if we are in this point, we can go to the pub and then we can go back to the class 3, to class 2, class 1. And all of this information in this graphical representation can be great in matrix presentation. So here we have the probabilities from to go from state C1, which is class 1, to class 2, or go to Facebook, which are these ones, or if we are in the pop, we have these probabilities here. So it's like just a representation at the end.
Yeah. That is the central part of all this. Only miss something, the reward. So that is the Markov decision process.
Here we have is just a Markov process, yes, but we have added some, and in this case is the actions. So we have a finite of set of actions,
Yeah.
and we probability matrix is going to take that into account. So the probability to go from one state to another depends on the state we are now and the action we take
And that is state.
in that state.
And also we have something new that is the reward.
The reward function that is this expected value from the reward, and is going to depend on the state and the actual action it takes.
X is a discounted factor or rate that is between 0 and 1. And we are going
To talk
to
about
later
later,
about that.
yes, in the next.
Well, we have only the reward one step. This is the reward I have in the state S with the action A. So something what we need to define is the total discounted reward. You know, that is the return.
And this is an amount that tell us uh, okay the total reward, but what we have here is the discounting rate.
Why?
So basically what he's doing is giving weight to the,
Future returns. You know,
but not the future at the end, just the next.
and next for that one step, two steps, three steps
Okay,
until final.
but at the end, the final returns are not going to be important for the reward.
Well, this depends. Well, yeah, this
Okay,
depends on
this
the
depends
value of
on the value you
the
define this.
discounted rate. Well, something important that is discounted. Maybe we can only take into account the total reward, but this is an infinitive sum
Yes, so
to make sure that this converts. We need a rate, discounted rate. One is one's reasons. And